So, let's begin our lab, Lab 4, which I like to call the Spring Lab. So, what are our objectives today? Well, we're going to observe and analyze the motion of a spring mass on a spring. We're going to build a computer model to represent it. We're going to use that model to illustrate our knowledge of the energy principle. And then we're going to answer a tricky question about periods on the sinusoidal oscillating waves. We can achieve these objectives through Tracker, Python, and Google Docs, and of course our brains. So here are some key equations before I show you the data. So we have Hooke's law, which is Ks times x, where x is displacement or stretch in this case, and Ks is a constant. And then we can find out Ks from 4 pi squared times the mass divided by the stretch squared. And then we can figure out the L based on the d minus the mass times the gravitational constant 9.8 on Earth divided by the Ks, and d is our specified distance, the distance of the oscillating wave, or you could say the amplitude of the oscillation. And then we have our kinetic energy equation, 1/2 mv squared, our trusty kinetic energy. Then we have our US, which is our spring energy, which is 1/2 the spring constant times the stretch squared. And then we have our potential energy, which is mgh on Earth, because that's what it is, I guess, where h is height. And then the total energy in the system would be the spring energy plus the potential energy plus the kinetic energy. Okay, so let's look at our tracker video. So if we play this video, we see that the mass moves in a circular pattern, but as we can see over here, it has a bit of oscillating pattern on both the x position over time and the y position over time. And this is actually illustrated through our Google Docs made graphs. And as we can see, the y position has an oscillating curve as well as the x position. So when we run the data in our program, which is programmed to have all the equations and everything put in, we can see that this is a bit slow, but we can see that the oscillations are there, and once we finish, we can see that there were some oscillations. And now if we have a graph of the energies over time, we can see the spring energy and the potential energy over time, as well as our kinetic energy. And when they all add up, they follow this virtually straight yellow line, which is a constant, which is an illustration of our energy principle. And so, going back to our PowerPoint, we can put it all together and say that the energy principle is satisfied, and that the total energy in the system is a constant at all times, since the kinetic, potential, and spring energies cancel each other out. If the y period were taken instead of the x period, the energy results would yield the same thing, although the graph might, the animation might look a little different, since we are taking a different time period and a different spring constant because of it. But essentially the graph of the energies would look fairly similar. They might not look identical, but there'd still be a constant total energy in the system, and thus we can conclude that the energy principle works in this scenario. So thank you guys for watching, and have a wonderful day.